Let's go over the test, chapter 6 radicals. We'll go through some of these problems real quick here and some quick explanations too. So let's look at this one here. Change to red. Simplifying radicals, you want to look for perfect squares that are built into them. So like this one is 25 times 3. 75 is 25 times 3. Looking for perfect squares that divide into 75. So the way you think about this is splitting it up into two separate radicals. Square root of 25 is square root of 3. So the square root of 25 is 5. Square root of 3, can't do anything with it, just leave it. So take that same process over here. Number 2. This time I won't rewrite it as 3 different things. I'm just going to take the square root of 100 by itself. Square root of 100 is 10. Square root of x squared is x, and the square root of y squared is y. So no need to rewrite it out in different things there. Just leave it like that. One other thing though, just keep in mind the square root of anything squared is just itself. Okay, so that's why the square root of x squared is just x. You can also think about it as if this is a square root, it's 2 root there, there's a 2 there, and we see how many times it divides into the exponent here and divides in once, or just x. Okay, so keep that in mind in the next couple problems here. Number 3, on this one, we're going to use that little property there. I am going to take the root, which is 3, and we simply just divide it in. We see how many groups of 3 of each of those x, y, and z's we can pull out of there. So it really just turns into a division problem. See how many times this 3 goes into 6 here. It goes in twice, so that's x squared. And we look at how many times it goes into our y to the 8th. It goes in twice, but there is a remainder of 2. 8 divided by 3 is 2, the remainder of 2, so 2 of those remain inside. It can only pull out a total of 6 to get me that y squared. And then with the z to the 12th, well, 12 divided by 3 is 4, so I can just write the z to the 4th out here. And that's it, as far as you can take that. Alternatively, if you had wanted to, you could use rational exponents on that, but it's just way easier just to do the quick division there. This one over here, number 4, if we split this up and we think about this as the square root of 25 times the square root of x to the 7th times the square root of y to the 6th, and we just do each one individually if you want to think about it this way. Square root of 25 is 5. Square root of x to the 7th, well, remember I'm seeing how many times in this case 2 will divide into that. 2 divides into 7 3 times, so that's x to the 3rd out here, but there's 1 left in there. I'm going to have a square root of x left over. And then when I go to the y's here, 2 divides into the 6th 3 times, so that's y cubed out here. That's it. Down here at these problems, and of course, pause at any time during this video, rewind, fast forward, you can jump around as much as you want on this recording. If it's in YouTube, you can speed it up too if you want. Number 5 here, so we're adding and subtracting radicals. So you got to think of the radical. In this case, they're all square roots of 6. Imagine that it's a variable, just like saying, like this is x and x and x, because they're all the same. You could say they're all x. So it's like saying, what's 3x minus x plus 2x? Well, that's pretty simple. I mean, we just add or subtract them all up, okay? So in other words, what's 3 minus 1 plus 2? And 3 minus 1 is 2, and 2 plus 2 is 4, so this is just 4 square root of 6. So just add up the coefficients. And remember, I'll get rid of this part here. Remember that you can think about this as being a 1 square root of 6 out in front there. Even though there's nothing there, I have 1 square root of 6. So the same thing on this last one here. They're all the same. Square root of 2, square root of 2, square root of 2. So I'm really just doing the problem of what's 3 minus 2. And that's negative 2. So I have negative 2 square root of 2 is left over. So combining like terms. 7 here we have some things that initially don't look like terms, but I could make some of them like into like terms, because this 54 here, if I think about, is there a perfect square that divides into that? Well, that is 9 times 6. There's a perfect square. This 24 is 4 times 6. There's a perfect square with the 4. And I think we've seen square root of 8 enough times to know that that's 2 square root of 2. So I can rewrite this that way. I can say that this is 3 times 9 squared, or square root of 9 times 6 minus 2 times the square root of 4 times 6. And then at the end, it's going to be minus 3 times 2 square root of 2. So when I go to my next step here, I can take the square root of this 9, that's 3 times 3 now, with the square root of 9 on the outside, which is 3, but there's still square root of 6 left over. This one here, I can take the square root of 4, so that's a negative 2 times the square root of 4, which is 2, and then there's square root of 6 left over. And this one here, it's going to be negative 3 times 2, which is 6 square root of 2. If I multiply these together here, I get 9 square root of 6 and minus 4 square root of 6 minus 6 square root of 2. So I have two terms that are like. Both these have square root of 6's in them. This square root of 2, I can't do anything with it, just leave it. But I can do 9 minus 4 for the square root of 6's, get 5 square root of 6 minus 6 square root of 2. So it's a little more complicated because I had to do a little bit with simplifying those square roots first, but once you do that, then things go together pretty nicely. Let's take a look at this one here. This is number 8. So we got 3 square root of 8, and then I got another square root of 8 over here. So there's two ways of doing this. If you want to put those square roots of 8 together first and write this as it's 3 plus 3, so that's going to be 6 square root of 8 plus 2 square root of 2. It's okay to do that in the first step, but square root of 8 we know is 2 square root of 2. So I can multiply this 6 times this 2 here, which is 12 square root of 2 plus 2 square root of 2. Now I have like terms with square roots of 2. I'm just going to do the 12 plus 2, which is 14 square root of 2. Okay, on the next ones, I got to do a little bit of multiplication on these ones here. So it's distribution. Okay, I just have to distribute this just like we normally would. So square root of 15 times the square root of 10. Remember, when you do that distribution there, you're really doing this, it's going to be square root of 15 times 10 underneath the same root. The same thing on this last one, it's going to be 5 times the square root of 2 times 15 under the same root there. So this is going to be square root of 150 plus 5 square root of 30. So we want to double check, are there any perfect squares that are factors of 150 or 30? So we can simplify this. You can't really do anything with a 30. It's just 2 times 3 times 5. There's no perfect squares in there. So that's done. We're done with that one. But 150 is 6 times 25, right? $1.50, 6 quarters. So I can look at this as 25 times 6 for that first one and take the square root of 25, which is 5, square root of 6 plus 5, square root of 30. And that's all you can do in terms of simplifying that. This one over here with 10, I'm just going to multiply these guys together. There's nothing I can do with the square root of 10 or square root of 6, so I'm going to put them together as the square root of 60. Just multiply them. But square root of 60 is 4 times 15. And if you're not sure, if you look at 60 and you're like, I'm not sure if anything divides into that, well, we've done this before. List off your perfect squares. I think everybody knows most of your perfect squares by now. List off a bunch of the perfect squares and then ask yourself, all right, is 60 divisible by any of these? And just go through that process. Obviously, it's only going to be divisible, well, in this case, it was 4, so it's pretty easy to do. And then we take square root of 4, which is 2, square root of 15. And that was it. That's all you had to do on that one. Can't go any further. These ones down here below were actually even easier than those ones, because square root of 2 times the square root of 2, I mean, you can look at that as it's going to be the square root of 4, which is 2. But we also know there's this trick that anytime you have the square root of something times itself, it just ends up being what was ever underneath the square root there. So could have looked at it that way and just said, oh, it's going to turn into 2, or multiply them together, get square root of 4, it's equal to 2. Of course, I mean, some people had square root of 4, but you got to simplify it. You get it all the way down to the most simplified form. Similarly, on this one over here, by themselves, 20 and square root of 5, can't do a whole lot with them, but when you multiply them together, you get 100. And of course, the square root of 100 is 10. Down below here, this first one, you had to FOIL things out a little bit. All right, so you're going to do the square root of 3 times the square root of 3, but hey, there's that little trick again that we just talked about up here. The square root of x times square root of x equals x, so therefore the square root of 3 times the square root of 3 equals 3. And then square root of 3 times 4, well, that's just plus 4 square root of 3. You can't really do anything with it. 5 times square root of 3, it's just 5 times square root of 3. 5 times 4 is 20. So now you just got to combine like terms. I can put together my 20 and 3, so that's 23. And then I can put together these two guys. They're both square root of 3, so I can add the 4 and the 5 to get 9 square root of 3. All right, that's the last of the square root simplification ones. Now we have some properties of exponents. So we are about to multiply these k's times each other. When you multiply, you add exponents. So really what I'm about to do here is 4, because it's just 4, can't do anything with it. This is 1. 1 times 4 is 4. And then the k, I'm going to combine these by taking 3 halves plus 7/4 power there. Okay, and I don't care if you do that on the side, it'll be a little scratch thing. If I find a common denominator, it's 6/4 plus 7/4, which is 13/4. So this just turns into 4k to the 13/4. If you're going to do this little scratch work, either put it on a separate sheet or way off to the side. You want to make sure it's not part of your work, okay? You can do that separately. All right, so going down to these other ones, 15 was kind of a gimme, n times n, that's n squared. Just add up the exponents, right? This one over here, though, you had to do some PEMDAS stuff. So before you could do anything with this n to the 1/2, you had to combine this first. But remember, when you raise a power to a power, you multiply those powers together. So I have to do 2 times 3 halves over here. So if we do 2 times 3 halves, remember, think of the 2 as 2 over 1. Then you can see, oh, these cancel out, it's just 3. So this just turns into n to the 1/2, oops, I put a quarter, n to the 1/2 times n to the third. Okay, so we're really done. Now we're at the point where we're going to add the exponents to each other. So it's 3 plus a half, that's 3.5. How do you write that as an improper fraction? Well, 3 times 2 is 6, plus 1 is going to be 7/2. So this is just equal to n to the 7/2. All right, this one here is a little bit more complicated, but notice right off the bat, we got this y to the 0. Whoops, that's not equal to 0. It's equal to 1. So I'm not even going to worry about that. But I do have to take care of this here first. But I have more than one thing in here. This is y times x to the 3/2. So I actually have to distribute this 2 times both of those. This is that rule. If we have x to the a times y to the b, raised to the c, it's x to the ac times y to the bc. We distribute that exponent on the outside. So it's going to be y squared when I do it times the raise the y to that power. But this one right here, think about this as 2 over 1. What's going to happen to the 2's? They're going to cancel out. It's just going to be x cubed, similar to that last problem. Then times x to the 1/2. And in fact, that's the exact same thing as that last problem too. I'm going to add these two up to get x to the 3.5, which is 7/2. Okay. 18 meant to be a gimme, meant to be the easiest problem on here because anything raised to the 0 power is equal to 1. So this whole thing was 1. You didn't have to do any of the work inside. Okay, these other ones, you had exponents on the bottom here. So remember on this one, this is x to the first on top. When you're dividing exponents, you subtract them. Or you're dividing like bases, you subtract the exponents. So I really just needed to figure out what, the 4 isn't going to go anywhere. It's going to stay on the bottom, but I'm going to be left with x to the 1 minus 1/2 on top when I cancel those out, which is, of course, just x to the 1/2. And that's it. This other one, kind of similar process. You can cancel out these. This is just going to be 1 and a 2. So I'm going to have just 2 left on top. And I have an x to the first at the bottom. So I'm doing 5/4 minus 1, but that's the same as 5/4 minus 4/4, which is just 1/4. So all I have left then is just x to the 1/4. And there's nothing left on the bottom. That's it. Your answer is just 2x to the 1/4. So these ones down here, first one, number 21, when you're solving an equation like this, you can look at it two ways. It's like you're taking the square root of the same thing on both sides. So these must be equal to each other. 22 minus 2n must be equal to 3n minus 8. Okay. Or you could do the trick of let's square both sides and drop the square roots. You get the same result. And the rest of it is just simply solving it. If you bring your n's to the left, you get minus 5n. If you subtract the 22, bring it to the right side, you get minus 30. Divide both sides by negative 5, you get 6. Now this one, number 22, you really just wanted to square both sides right off the bat. Square the left, square the right. Don't forget to square that too, though. And you end up with m over 7 equals 4. Now all you have to do is multiply both sides by 7, and you get m equals 28. And you should double check that these answers work by plugging them into the original. So checking for extraneous solution, because sometimes you do get a solution that doesn't work, which will happen up here in the next couple of problems. Let's look at this first one here. We're at a point where we really just need to square both sides. So it turns into negative 4 plus 5p equals p squared. This p squared kind of tips me off to that this is going to be a quadratic form. I need to set it equal to 0. So I'm going to bring everything to the right-hand side. I don't want to have a negative p squared, so I'm going to bring everything to the right. So it ends up being 0 equals p squared minus 5p plus 4. And whenever you have a quadratic, if you can solve it to factor it, by all means do that. This ends up being p minus 4, p minus 1. Get that negative 5p in the middle and the plus 4 at the end. So p is equal to 4 and 1. And if you check both of those, they both work with the original equation, no extraneous solutions. Now 24, you didn't actually have to do any work if you recognized right at the beginning that you can't take the square root of something and end up with a negative. So this one is just simply no solution. If you did go through the process of square both sides, square this, and you ended up with x minus 2 equals 25, so x equals 27, and you checked it, you would have found up here, if you look at the original, if you put a 27 in for x, you get the square root of 25 equals negative 5, and then right away you realize, like, oh, that doesn't work. I can't take the square root of 25, get a positive, or a negative 5, it's going to be positive. So either way, extraneous, no solution, even if you just didn't even have to do any work on it. You started right there. Inverses. So remember, the trick for finding an inverse is you first rewrite. You rewrite it as, instead of g of x, you write it as y, and so 2 over x plus 1. You swap your x and y, so we're going to do a little swap here, x and y, and turn this into x equals 2 over y plus 1, and then we just use algebra to solve for y. Okay, so one way to do this is multiply both sides by y plus 1. Okay, cancels out those. And then, so I'll just rewrite this next step here. We've got y plus 1 times x equals 2. Now I want to get rid of that x, so I'm just going to divide both sides by 2, or by x rather. So I end up with y plus 1 equals 2 over x. So now I can just subtract a 1 from both sides to get y equals 2 over x minus 1. And this is our g inverse of x. All right, so those are the steps. Swap x and y, solve for y. That's pretty much it. But you got to have some algebra skills in order to do that. 26 was actually easier on this one. You swap your x and y, or we'll rewrite it first. Y equals 2x minus 4. Swap our x and y, so x equals 2y minus 4. Now solve for y. I'm going to bring the 4 to the other side, so it's x plus 4 equals 2y. Divide everything by 2. So you end up with y equals, like, you can just leave it as this. You don't have to split it up if you don't want to. If you did, it'd be x over 2 plus 2. And this is our h inverse of x. All right. Come down the home stretch here. State if the given functions are inverses. Make sure to show the work to support your answer. So this is simply a yes or no question, but you got to support it with some sort of work. So one way to do it is, remember that if we can show that g of f of x simply equals x, then their inverses. In other words, this is plug in f of x into g of x. So if we do that, if I take this whole thing and I just plug it into this x here, so g of f of x, it's going to be a negative. Now replace the x with a negative 4x plus 3. That's what this was here. But then rewrite the rest of g of x. So there's a plus 3 and there's a 4 on the bottom. Okay? And then we just simplify it. And if we end up with x, then they're inverses. So this turns into, it'll be 4x minus 3 plus 3 over 4. If I distribute that negative sign in there. 3's cancel out, and I'm just left with 4x over 4, which is indeed x. So it checks out, so we can say yes, that they are inverses, and that would be enough work to prove it. Alternatively, you could have taken either g of x or f of x and find the inverse of it, and if it matches up with the other one, that works too, but this is kind of the preferable method, do it this way. All right, graphing this function. So remember, general form is y equals a x minus h, or square root of x minus h, rather. Square root of x minus h plus k. So the h and k is the starting point for the function. Okay, so in this case, our h here is a negative 2, and our k is a negative 3. So basically, we're going to start at negative 2, negative 3. Now, if you didn't remember to do that, so that's our point down here, I'll put it in red. That's our starting point. If you didn't remember that, you could also just look at this and say, well, if I'm going to try some x and y values, the smallest x value I can put in without this being square root of a negative is a negative 2. And all the other points are above that. Okay, so negative 2 does get you negative 3. But then we can plug in some other values in here. And remember, the trick for this is picking numbers that are going to get you perfect squares. So my next perfect square would be 1. Underneath here, if I want to get 1, then x would need to be a negative 1. All right, and if I put in a negative 1 there, I get a negative 2, just plugging it in. The next perfect square is 4, so if I wanted that, I'd want to plug in a 2. Okay, so if I plugged in a 2 here, it'd be 2 plus 2 is the square root of 4 minus 3, which would give us negative 1. And that's usually enough to plot this out. These would be our points looking like this, and shape's going to look something like this. Kind of missed that one there. All right, so that's all I was looking for on that one. Yeah, when in doubt, just start plugging some points in, basically. And which was kind of the case on these here. On each of these, if you knew that HK thing, you could look at this and say, all right, my H is 0, my K is negative 5. Which one of these starts at 0, comma, negative 5? Well, this one does. This one doesn't. This one starts at 0, positive 5. This one doesn't even look right at all. So yeah, answer was just A. Okay. This one over here, it says the plus K on the outside is 0. So my X is negative 6, or my K is, rather, my H is negative 6, comma 0. So I'm looking for a starting place of negative 6, 0, which is only this last one, D. That's the only one that starts down at negative 6, 0. Okay, and then lastly, the bonus. I'll just mention it really quick here. I talk about this in class, but just work these from the inside out. Figure out first, what is the square root of x to the 600? Well, remember, this is a square root. We just got to divide 600 by 2. So that gets us x to the 300. So now I want to take the cube root of x to the 300. 300 divided by 3 is 100. Then I want to take the fourth root of x to the 100, which is x to the 25. You see where we're going with this. And the fifth root of x to the 25 is x to the fifth. So this whole thing is equal to x to the fifth. To do it a little faster, you could have just started here and said 600 divided by 2 is 300, divided by 3 is 100, divided by 4 is 25, divided by 5 is x to the fifth. You can actually do this problem pretty fast. All right, so that's it. Make sure you understand these for the retake. And if you got any extra questions or would like some extra problems to try out, just let me know.